Hi Year 12s, in this video I'm going to show you how to prove this cosine rule. The only skills you need to be able to prove the cosine rule are you need a bit of basic algebra manipulation, you need to know how to use Pythagoras, and then thirdly you need to be able to use SOHCAHTOA. So the fact that you're in Year 12 means you can do all three of those things, so that should make this proof pretty easy. Right, so the first thing we're going to do is we're going to start with the scalene triangle ABC. And as mentioned earlier, you're going to be using Pythagoras and SOHCAHTOA, so you know that we need some 90-degree triangles. So the first thing you're going to do is you're going to drop a perpendicular height from B, and we're going to call that H. Okay, so now you should see two right-angled triangles, and the other thing that we just quickly need to sort out is that if we've got two right-angled triangles, we need the bases for the two 90-degree triangles. So I'm just going to introduce another variable. I'm going to call that length there x, and then if the whole base length AC was b, and that piece now is x, then obviously the remainder would be b minus x. Okay, so now we're going to start in the right angled triangle over on this side. I'm just going to circle that one there. And all we're going to do is we are going to make a statement using Pythagoras. So using Pythagoras, I think everyone here will be quite happy for me to say x squared plus h squared equals c squared. Okay, now if I shift across to the right angled triangle that side, I can now also make a statement using Pythagoras. And this time, I think you'll all be happy with me saying b minus x squared plus h squared equals a squared. Right, so the next step in this proof is to look at what I've written down, and we'll notice that in both of them, we've got an h squared. So what I'm going to do is I'm now going to rearrange both of those to get h squared on their own, and then I'm going to equate the two, set the two equal to each other. So over here on the left hand side, I can say h squared is equal to c squared minus x squared. And over here on the right hand side, I can say that h squared is equal to a squared minus the bracket squared, which was b minus x. Now if h squared equals c squared minus x squared, and it's also equal to a squared minus that bracket squared, then surely using simultaneous equations, I can now make the statement that c squared minus x squared is equal to a squared minus b minus x all squared. Right, so our next step is obviously now to manipulate this. If we cast our eyes up here to what we're actually trying to prove, clearly we want to get a squared on its own, and we definitely don't want this bracket of b minus x squared. Now, your biggest danger here is that when you multiply out the bracket, you forget that it's minus the whole bracket squared. So quickly multiplying that bracket out, we get b squared minus 2bx plus x squared. So because there's a minus in front of that bracket, when I multiply that minus in, I end up with minus b squared plus 2bx minus x squared. So let's get a squared all on its own, because that's what I'm trying to prove up here in this formula. And we may as well leave a squared on its own this side. And then I've got, if I bring the minus b squared over, I've got b squared plus c squared minus x squared and minus 2bx plus another x squared. Right, so just simplifying that, everyone's happy how that minus x squared and plus x squared cancel off. So now I have a squared equals b squared plus c squared. It's all looking good, just like what I'm trying to prove. And then I've got minus 2bx. So that's what I've got there in pink. Up here is what I'm trying to prove. And the main thing that I notice is that I've got this little x over here, which is not actually in the final formula. So what we now need to do is we need to refer back to the original triangle. Okay, so just getting rid of some of the clutter from the previous slide. That's how far I've got. There's my original triangle. and we've just discussed that this x over here is not what we want. So we look back to this original 90-degree triangle here on the left, and this is now when we use SOHCAHTOA. So I think you'd all agree that this is angle A over here in the corner, and we can say, seeing it's the cosine rule, we may as well use cos. We can say that cos A equals adjacent over hypotenuse, which is x over c. And rearranging that leaves me with c cos A equals x. And it's as simple as I now put that in place of that x there. And therefore, a squared equals b squared plus c squared minus 2bc cos A. And that is the proof of the cosine rule. I hope you've managed to follow what I've done. If anyone wants to buy me a present, you're welcome to get me one of those fancy pens so my handwriting's not so bad. The good news for some of you is that you don't actually have to know the proof of the cosine rule, but it does give you a little bit of a background into it and a deep understanding, which would hopefully make your general knowledge of using the cosine rule a little bit better. Right, thanks.